Have scientists finally discovered alien life? Well, you may have seen many such reports on news channels recently. But is it really true?
Strongest evidence yet of life.
Planet 124 light years away could be home to life.
Scientists detected gases in the atmosphere that on Earth only come from living organisms.
We are not alone in the universe.
Don't you feel something is off whenever you hear such claims? Meet Nikku Madhusudhan, a graduate scientist from IIT Varanasi, who, along with his team at Cambridge University, discovered a planet called Kepler 2-18B, where there is a strong possibility of alien life. Even great scientists like Stephen Hawking, Enrico Fermi, and Nikola Tesla died waiting for this moment. But hasn't this kind of news become very common these days? Every year, there is news like this. Alien life finally found, be it a planet like Proxima Centauri b, planets of the TRAPPIST-1 system, or LHS 1140b, and how can we forget Kepler 452b, which was called Super Earth, which is even better than Earth in supporting life. But still, the undisputed fact is that till date, we have not found any evidence of alien life. So this discovery made by Nikku Madhusudhan on Kepler 2-18b planet, is this also just hype, or has something truly big happened this time? Well, when I did a detailed research on this, I personally confirmed 3 very significant discoveries. And these discoveries, trust me, are unlike anything we have ever seen before. In fact, we have never even come close to anything like this before. One of these is that we may have found the molecule of alien life. On the 7th of March, 2009, at 3:49 a.m., NASA launched the Kepler Space Telescope into space. It was deployed in the Sun's orbit instead of the Earth's orbit because it was not going to be an ordinary telescope, rather it was going to maintain a distance and discover such planets hundreds of light years beyond, which are very similar to our Earth, and those in which there is a high possibility of alien life. And so that the Earth does not block its view, it was deployed in the Sun's orbit. From 2009 to 2015, the Kepler telescope kept staring into the infinite darkness of space without blinking, to capture some specific movements. This movement was the dimming of the light coming from a star, because this can indicate that maybe a planet passed in front of that star, blocking the light coming from that star. Do you know the incredible things Kepler can see? Imagine if even a fly comes in front of the light emanating from the headlight of a vehicle traveling 1000 km away. Then even if the brightness is dim, it will be captured by it. Kepler's eyes witnessed that the universe is full of planets, which exist in much greater numbers than stars, whereas earlier we knew about only a few planets. But then, just 4 years later, unfortunately, in 2013, Kepler had a major accident. 2 out of its 4 reaction wheels got damaged one by one. Now, reaction wheels are pairs of spacecraft which help in changing the direction of the telescope and provide stability, like the steering wheel of a car. But without minimum 3 reaction wheels, Kepler telescope could not point stably at any patch of space, and the mission had almost failed without the discovery of any significant alien planet. On applying a very creative mind, engineers found a brilliant solution. They used the pressure of the sun rays coming from one direction for stability, just like a kayak does in water current, and the mission was saved. But this meant that ever since, the Kepler telescope would be able to keep an eye on only a limited space area. And because of this limitation, NASA redefined its mission in 2014 and decided to keep an eye only on red dwarf stars. This new mission was named K2 mission, and where previously only Kepler or K used to be added before all the discovered planets. Like after Kepler 22b was discovered in 2014, K2 started being added before the names of planets. K2-18B, our today's hero planet, was discovered just 1 year after this. In 2015, the telescope detected this planet revolving around a red dwarf star K2-18 every 33 days. And since this planet was the second nearest planet to our star K2-18, it was given the code K2-18B. B means the second planet from its sun. Now pay attention, because the next story will tell you how understanding a planet so far away from 124 light years makes even the scientists sweat, and how big mistakes are made. After studying the initial data sent by Kepler, it was found that this planet is of such a type of planet which is not present in our solar system. It was called mini Neptune type planet because its radius was 2.6 times more than the radius of Earth and mass was 8.6 times more. Now, if the size is so huge, then its volume should be 17.6 times more than Earth, but the mass is only 8.6 times more. Its mass indicated that this planet is neither made mostly of solid rock like Earth, nor mostly of gas like Jupiter, whose density is slightly lower. So what could this light material be? Water? And that is why this leading theory came out that perhaps this planet is wrapped in the sheet of a huge and deep ocean. But after doing the calculations by factoring in the distance at which K2-18B was orbiting from its red dwarf star, the average temperature of this planet came out to be -8 degrees Celsius. So, did the snow put a damper on our hopes of getting water? You will see how the life of scientists is like a roller coaster ride, in which they have complete blind faith that this ride will definitely take me to my destination, no matter how many hurdles come in the way. And so the scientists thought, what if the atmosphere of this planet is such that it acts like a sheet and brings the temperature of K2-18B above 0 degrees so that the water can remain in liquid state. But for this, it was very important to find out the atmosphere of the planet and what it was made of, which was clearly beyond Kepler's ability. And that's when our second hero entered the picture, the elder brother of Kepler, the Hubble Space Telescope. The Hubble Space Telescope was deployed into space back in 1990. And it works like a giant microscope floating in space, capable of capturing detailed, high-resolution images of any space object. But the most special thing about Hubble is that it can capture these images in different spectrums and wavelengths of light, like ultraviolet, infrared, and even in normal visible light form. Okay, so how can we possibly find out what this distant planet's thin atmosphere lying 1,170 trillion kilometers away is made of? Well, get ready to be mind blown. Remember, K2-18B completes one orbit around its star every 33 days, right? Now, when this planet passes in front of its star, the starlight shines through its atmosphere from behind. At that exact moment, if we capture a focused and detailed image of its atmosphere in different light wavelengths, some parts of the light, meaning certain wavelengths or spectrums, will get blocked after interacting with the particles present in that planet's atmosphere before reaching the telescope. This happens because atoms and molecules of different elements absorb only specific wavelengths of light, those that match their energy levels. And based on this, we can accurately measure which elements might be present in that planet's atmosphere. For example, do you see this wave here? This is electromagnetic radiation, which is just the scientific name for light. Yes, light travels like a wave through space. But why does the distance between its two peaks keep increasing? Well, the nature of light is such that its wavelength keeps increasing as the light wave travels longer distances. Kind of like the light wave gets stretched, and the more it stretches, the more its wavelength, and as a result, its energy levels change. So look here, this same light wave starts from its most powerful form, gamma radiation, and then slowly transforms into X-rays, UV rays, visible light, infrared, microwaves, and finally radio waves as it stretches further and further. Now notice, every type of radiation has its own specific wavelength. For example, ultraviolet light ranges from 10 to 400 nanometers. Visible light, which we can actually see, ranges from 400 to 700 nanometers, and so on. With increasing wavelength, now let's say that the atmosphere of K2-18B blocks or dims light specifically at the wavelength of 589 nanometers. This would mean that sodium is present there, because scientists know from quantum mechanics experiments that the energy levels of sodium atoms perfectly match the energy of light at 589 nanometers. If it blocks or dims ultraviolet light at 121.6 nanometers, then hydrogen is present there. 770 nanometers for potassium and 1400 nanometers for water vapor, that is, water. And list goes on. Through this, we can detect the unique fingerprint of every single element and molecule. This brilliant method is called transmission spectroscopy, which literally tells us a great deal about a planet's composition even while sitting billions of miles away. So, Did Hubble succeed? Well, in 2018, Hubble was the first to claim the presence of water vapor, that is, water on this planet, which was a huge discovery. But was the universe really going to reveal its secrets so easily? Hubble's capacity was limited. It could only observe in the infrared frequencies between 1100 and 1700 nanometers, a range where water vapor molecules overlap a lot with methane. And that's why, what if what we are assuming to be water is actually just methane gas? Many scientists raised such questions, and this is where we soon realized that this data could not be fully trusted. We were going to need more advanced equipment, ones that could study a much wider spectrum of light, so that such measurement errors would not happen, and the stage was set for the launch of humanity's most advanced creation into space, the James Webb Space Telescope. But before we find out exactly what secrets James Webb uncovered, let's pause this story for a moment because on the other side, something even more interesting was happening. None other than our Indian origin scientist Nikku and his team had come up with a brilliant concept. Nikku had observed very weirdly interesting things in the universe, like planets such as K2-18B. These mini Neptunes are found in huge numbers across the cosmos. They are extremely common because red dwarf stars themselves are very common. So why couldn't it be possible that such worlds also have a chance of supporting alien life? Why are we focusing only on rocky planets like Earth? And then, after studying many such mini Neptunes, Nikku noticed some common traits among them. These planets usually have wide, deep oceans, and their atmosphere is covered by a thick layer of hydrogen gas, which keeps the planet warm. Nikku and his team even gave these planets a brand new name, Hycean worlds, combining hydrogen and ocean worlds. And according to Nikku Madhusudhan, the planet K2-18B fits perfectly into this Hycean model. According to Hycean world models, imagine a planet whose atmosphere is dominated by hydrogen and helium. Means at least 80 to 90% of its air is made up of these gases. Along with that, there could be small amounts of water vapor due to a vast ocean, methane, carbon dioxide, carbon monoxide, and ammonia. Now, to support this model, Nikku predicted that on such worlds, the amount of ammonia should be extremely low because ammonia easily dissolves or sinks into water. So just think about it, a world not filled with oxygen, but with hydrogen. On such a planet, you could have life forms that actually breathe hydrogen, similar to some extreme microorganisms on Earth. And since hydrogen is also a greenhouse gas, it can act like a blanket, trapping heat and keeping the ocean water in a liquid state. This ocean could be hundreds or even thousands of kilometers deep. Just imagine, on Earth, our oceans are only about 10 kilometers deep at most, and even there we find bizarre deep-sea creatures. So, what kinds of alien life could evolve at pressures 100 times greater? But for life to exist, some things would need to stay in a delicate balance. For example, the hydrogen blanket around the planet shouldn't be so thick that it turns the whole world into something like Venus burning up in its own atmosphere. And if the ocean is extremely deep, the pressure could be so intense that water would transform into exotic forms of ice like Ice 6 and Ice 7, which have unusual properties almost like clay. Thick layers of such ice could form a barrier between the ocean floor and the liquid water above, preventing life from emerging the way it did on Earth. Here on Earth, life got its first energy boost from hydrothermal vents, underwater volcanoes that provided the right conditions for life to spark into existence. But on such water worlds, there could be many other unique ways for life to emerge, and scientists have actually demonstrated some of these pathways in real experiments. Take the famous Miller-Urey experiment from 1952. Scientist Stanley Miller took a mix of simple chemicals and literally zapped them with electricity to simulate lightning, triggering reactions that produced 20 different organic amino acids. And which elements were these? Exactly the same ones found abundantly on Hycean worlds: hydrogen, water vapor, and methane. Electricity was used as an energy source because lightning and thunderstorms are common on many planets. So, could raging lightning storms have actually sparked life into existence on such a world? Scientists have also combined UV rays, hydrogen cyanide, and certain minerals to create parts of life's essential molecule, RNA. So, there could be countless pathways for life to take shape, so many that they are beyond our imagination and current knowledge. Now, here's an important point to note. Up until this point, that is 2021, we didn't have any confirmed evidence about what K2-18B's atmosphere is actually made of. Nikku's team had built a purely hypothetical model. They used the principles of science to create a simulation to answer one big question. In theory, what are the chances that life could exist on a planet with these unique characteristics? Now, this was crucial because theory makes predictions about what we might find on such a planet, which can then be tested and confirmed by powerful telescopes like the James Webb Space Telescope. And if theory and evidence match, then it means we are truly seeing reality as it is. That's the beauty of science. We need both explanation and evidence, theory and proof working hand in hand together. So did K2-18B live up to Nikku's bold predictions? 8th of January 2022, a technological marvel costing around $9 billion. The James Webb Space Telescope was deployed into space. Think of this telescope as Hubble's ultimate upgrade. If Hubble is like a black and white television, then James Webb is a full-color, high-definition television. If Hubble could barely read a few hidden words from the universe's secrets, Webb can read entire paragraphs. Because remember, Hubble can observe a tiny portion of the infrared spectrum, roughly from 100 to 2500 nanometers. But James Webb can observe light frequencies from 600 to a massive 28,000 nanometers. Thanks to its wide infrared range, we can measure key elements such as water, methane, carbon dioxide, and ammonia with great clarity. Webb can also detect more complex biosignatures, direct clues that hint at life, including molecules like DMS, dimethyl sulfide. And here's the best part. Webb's mirror is about 2.5 times larger than Hubble's, which means it can capture 6 times more light. Plus, it's 100 to 1000 times more sensitive because it operates at an extremely low temperature of around minus 233 degrees Celsius. So it doesn't generate its own electromagnetic noise. This means incredibly detailed, high-definition, high-precision, and crystal-clear images. If any instrument could present evidence of alien life, it was this one. The moment it was deployed, the James Webb Space Telescope sprang into action, and by mid-2022, it had already locked its gaze onto K2-18B. These observations continued for almost a year, and finally in September 2023, the results came in. The James Webb Telescope confirmed the presence of methane, carbon dioxide, and yes, even a faint hint of DMS. At first, Nikku and his team could hardly believe it because this was massive news. Let me explain why. You see, until now, in all the so-called potentially habitable exoplanets we've found, we've never detected DMS dimethyl sulfide anywhere. And DMS is special. On Earth, it's produced exclusively, and I mean exclusively, by marine life, like algae and plankton, in any measurable amount. It's the chemical behind that distinct ocean smell you catch when you're near the sea. Sweet, oceany, cabbagey, and a bit sulfury. Apart from DMS, there's really no other molecule we know of that can so unambiguously hint at the presence of life. No other biosignature even comes close. Think of it this way: finding methane is like the universe whispering in your ear. But finding DMS is like it shouting directly at you. But of course, it was crucial for Nikku and his team to make absolutely sure they'd really detected DMS, that there was no measurement error or false signal. So they didn't stop there. The first detection had been made in the lower infrared spectrum, about 800 to 5000 nanometers. Now, they decided to observe the medium infrared range from 6000 to 12,000 nanometers to confirm it. Because if DMS truly exists in K2-18B's atmosphere, it should consistently appear in both the low and medium infrared spectrums. After several more months of observations, just a few days ago, the final results came in. Once again, the James Webb Telescope confirmed that yes, K2-18B really does have DMS or DMDS, which is a similar molecule present in significant amounts. How significant? Well, thousands of times more than what we have on Earth, which is huge.
Now, scientists have found the strongest evidence yet that a planet 124 light years away could be home to life. Researchers detected molecules in the atmosphere on the K2-18B, which on Earth are produced by marine organisms.
If Nikku's Hycean world model is right, and if alien life is indeed the source of all that DMS, then that entire planet could be a vast ocean world teeming with some form of plant-like life. And who knows, evolution there might have given rise to entirely new kinds of water-based creatures that we've never seen or maybe can't even imagine. No alien mission so far has given us a breakthrough like this. Right now, there's an incredibly strong possibility, a real chance, that alien life could actually be thriving out there. But there's still more work to be done before we get to see the final climax of this story. More evidence needs to be gathered, and trust me, Nikku and his team are probably too excited to even sit still right now. Because if this discovery turns out to be true, their names will go down in history forever. Look, James Webb Telescope has indeed detected the presence of DMS, but the evidence we have right now has an accuracy of about 3 sigma, which means it's 99.7% reliable. Still, there's a tiny 0.3% chance that the signal could be due to some random fluctuations. Now, in scientific community, any major discovery needs to be backed by 5 sigma level evidence. That's about 9.999994% certainty that the result is real. And that's why Nikku and his team will need a bit more time with James Webb Telescope's measurements to push this up to gold standard of 5 sigma, which in my opinion is now more of like a formality than a real hurdle. But the biggest thing that we still need to confirm is this: there truly is no other source of DMS on this planet. K2-18B. Extremely high amount of DMS that we have detected. What if it has a completely different source that science has not yet understood? For example, in some lab experiments, scientists have managed to produce DMS by exposing a mix of UV light and gases like hydrogen sulfide, methane and carbon dioxide, all without any biological processes involved. And DMS has been found on some comets too, though in very tiny amounts. On the other hand, Nikku and his team are quite confident that according to Hycean world model, K2-18B is a perfect match and that life is the only viable source. They argue that other mechanisms just couldn't generate so much DMS on their own. Still, if we did find a completely non-biological source for this much DMS, that in itself would be a huge scientific discovery. That's why some scientists are asking uncomfortable but necessary questions. Should we really rely on DMS alone as definitive proof? After all, if there is even a 1% chance there is another explanation, shouldn't we be absolutely sure? And there's one more missing piece in this puzzle. So far, scientists haven't found any evidence of ethane in K2-18B's atmosphere. That's puzzling because according to the model, wherever DMS is present in significant amounts, ethane, a common byproduct, should also be found in large quantities. This raises a few big questions. Is our transmission spectroscopy model incomplete? Or could our detection methods themselves still be inaccurate? So basically, a full-blown debate has erupted across the entire scientific community, just like it does with every big discovery. And all this confusion might only be cleared up in the next report, where Nikku and his team will focus on a few key areas. Number 1. Confirming the presence of DMS at the 5 sigma level, the gold standard of certainty. Number 2. Detecting ethane which should exist as a byproduct of DMS. Number 3. Ensuring the consistent absence of ammonia. Number 4. Differentiating clearly between DMS and DMDS. And finally, number 5. Searching for other organic or sulfur-based compounds that could make it clear whether the DMS really comes from life or from some exotic non-biological source. But do you know what the most important and eye-opening lesson here is? Look, the James Webb Space Telescope isn't Nikku's personal backyard telescope that he can just point wherever he wants, whenever he wants. Using it requires going through a rigorous approval process with long waiting periods and intense competition. And in science, making a groundbreaking discovery is never as simple as snapping a photo and finding the truth. In fact, the work done behind the scenes, refining theoretical frameworks, conducting lab experiments, and improving computer models is just as important, if not more so, than the telescope observations themselves. And all of this has to happen in parallel. The Hycean models need to be studied more deeply. We have to simulate the planet's atmosphere, climate, and chemistry in far greater detail to truly understand its complexities and make better predictions. In the lab, we have to keep searching for other ways DMS could be produced without life, so we don't chase down the wrong path. And besides the Hycean models, we need to develop alternative models too, ones that might fit K2-18B's characteristics even more accurately. So just imagine how much effort goes into a single discovery. how many directions scientists have to work in all at once, and how many failures they have to face along the way. Wouldn't a scientist feel demotivated in the middle of all this? Well, absolutely not. In fact, that's exactly what fuels a scientist's engine. Curiosity, unsolved mysteries, hidden links, secrets slowly coming to light, that feeling of standing right on the edge of a monumental discovery. This is what every scientist lives for. It's that instinct, that spark that makes us truly feel alive. No matter how dark the path may be, no matter how invisible the destination may be, the light of curiosity always has guided us forward. We may be smaller than the stardust, but within us burns a fire greater than all the stars combined. Because in this endless darkness, we are searching for the faintest spark. Amid the roaring storms of radiation, we are listening for a single heartbeat of life. That heartbeat may not be made of blood like ours, but even a single echo of it will change human history forever. It will rewrite the pages of faith, redraw the lines etched in our palms, and perhaps in finding it, we might rediscover our lost humanity. Maybe, just maybe, we will erase the boundaries that divide us, stand united, and carry our civilization to new heights together. On the note of unity and peace, Gaurav Thakur signing off, and as always, stay curious and stay human.